Well, welcome everyone to the May 2021 SNOC webinar, Coming Out of Drought, Making the Most of Soil Water by Sean Murphy, brought to you by the New South Wales DPI Soils and Water Unit. Now, more to the fun. I'd like to introduce Sean Murphy, who's presenting today's webinar. Sean is a senior research scientist focused on increasing water productivity in rain-fed grazing and cropping systems. The primary aim of his research program is to identify processes and mechanisms within pasture systems that enable increased water use efficiency to generate more product from each millimetre of rainfall we receive. His advances in hydrological science allow primary producers to better manage tropical perennial grasses and legumes in the summer-dominant variable rainfall zone of New South Wales. This includes making informed decisions about future pasture growth and management actions. His ongoing scientific investigation program aims to increase water productivity in rain-fed grazing systems, funded by the Livestock Productivity Partnership, building upon more than 20 years of close collaboration with Meat and Livestock Australia MLA. And Sean's selling himself a little bit short. He's left out that he has extensive experience prior to this last career in the rangelands of New South Wales, and Sean has a wealth of knowledge there. So if I haven't embarrassed you too much now, Sean, I'll hand it over to you.
Okay, first of all, well, thank you everyone for joining in on the webinar today. I appreciate you taking the time to participate and obviously take the time to answer that poll question. Intriguing. About half of us think that we're out of drought wherever you are. I do certainly hope that is the case. Some areas have received fantastic rain, others are probably still trying to catch up a little bit. But it's great to see a wide-ranging audience in the room, and without further ado, let's get into it. So this slide is just an introductory slide, just gives a general introduction about the outline, structure of the presentation that I'll go through. Firstly, I want to go through a couple of definitions to give some boundaries as to where my presentation sits. All of what I will be presenting comes from the perspective of pasture systems rather than cropping. So my apologies to those of you in the room who have a specific interest in cropping, but I hope you pick something up that's useful anyway. I'll discuss our climate in Northern New South Wales, and again, the presentation's coming from that perspective, so hopefully you'll pick up something from that as well. I'll discuss just how variable it is and work through how I can use the soil water balance to give us some ideas of where we're sitting and what we're doing, and show how, even among all this variability that we go through, how we can use the soil water balance to let us know where we are and give us some indication of looking forward. And after working through a fair bit of that background type stuff to get us all on the same page, I'll then go through a couple of the examples of the pasture responses coming out of drought. And hopefully, and among all of that, hopefully I achieve to convey some key concepts that everyone can take away as some take-home messages. There are a couple of other poll questions later on in the presentation, and I'll be intrigued to see how the responses go there, and also for your own interest. So some definitions. There's a lot of text there. I won't go through all the definitions. Read them at your leisure from the recording, or take a screenshot so you can digest them later. The definitions are really there to provide the context of what I'm working through. But the first one is probably the one that I do want to spend some time on, and just go through that. So talking about pasture systems, soil water content is the most closely linked cause of agricultural drought. So not the rainfall per se, but definitely the soil water store. When the soil water store is short, the pasture growth declines. And that came out of work by Greg Lodge and Ian Johnson back in 2008, which was a very interesting study. And that study produced this panel here, which shows a series of histograms for the distributions of the types of droughts. So short seasonal droughts on the left-hand bar, running through to intermediate, moderate, severe, exceptional, and extreme. The key features I want to point out on this panel is that the southern Mediterranean style environments like Albany in WA and Hamilton in Victoria, the droughts that they experience are dominated by these short seasonal style droughts, which is typically the summer autumn period in those environments. While moving into New South Wales and indeed northern New South Wales, and using Barraba as an example, we still have quite a few of these short seasonal droughts, but it's the right-hand side of the histogram where we can see an abundance of extreme and exceptional droughts which extend over many months and sometimes years, which is not unlike what we've just experienced. So really, the drought that we've just been through for our part of the world is not that uncommon for us, but it presents major challenges for us in how we manage our pasture systems. So that's looking from the perspective of soil water, and I wanted to get that down first and foremost. A common way that people interpret the drought that we're in at any given time is the surplus or deficit of rainfall. Now, there's a lot of data on this table, but it's quite simple when we work through it. So this column here has a durations of 3, 6, 9, an increasing number of months. And what the values are the accumulation of rainfall, monthly rainfall totals up to the end of December 2019, which is probably the peak of the drought. So we can see how much rainfall we would expect as a median value in the second column across. We can see how much rainfall we physically received for each of those durations in that third column. The total as a percentile of all the numbers throughout the whole record, stretching back to the 1800s. And the final column shows us the deficit that we experienced. So when we look at the 12, the 24, and the 36-month durations, we can see that Tamworth had a deficit of minus 392 millimetres, minus 659 millimetres, and minus 687 millimetres. So for those 2 and 3 year periods, we were missing a full year's worth of rainfall in our environment. So the extent of those deficits and the reality of the percentiles, so 0, 0, 1, 0, 0, 0, you can just very quickly see how much rainfall we were missing from what we expect on average, making the recent drought exceptional indeed. So from those previous two slides, I hope I've given you an impression that in northern New South Wales at least, it seems we're always either not far away from going into a short-term drought, or it seems we're in the middle of a long-term exceptional drought. And from the measures that I've made over the large number of years in this environment, measuring soil water content, what I've seen is that our soil water stores can deplete from being full to completely empty in as few as 6 weeks. So that makes it incredibly challenging for our pasture production systems in this environment. We're frequently coming out of a drought, and quite rapidly it seems we're entering back into one. So trying to, the objective that I often convey for our pasture systems is actually to maximize how much rainfall we capture and make good use of it in this summer dominant rainfall environment to try and make the best pasture production that we can. And obviously, if we're looking at growing livestock, we want to provide those livestock with sufficient quantity and quality to meet whatever their intake requirements are for that class of animal. So looking at the climate of the Northwest Slopes, Tamworth area, I just want to present this panel to show the monthly distribution of rainfall. And the thing I want to point out to everyone in the room is just the U-shaped nature of that distribution, just reinforcing the summer dominance of our rainfall pattern. The average or the mean rainfall is around 650 millimetres, and the median is a fraction less. Now, while those bar charts look quite uniform, that's fantastic, but the reality from year to year is vastly different. So this panel, I want to draw your attention to the red trace that's on this figure, and which shows the current status of the rainfall accumulation over the past 12 months to the 3rd of June at one of our research sites just north of Tamworth. And as you can see, for a 12-month accumulation to the 3rd of June, we're actually sitting on the 4th highest total in the entire rainfall record for that site, for that locality. That sounds fantastic. However, the reality for the pasture growth and the pasture production is quite the opposite. Stored soil water levels at that site, we know from our measurements, have depleted rapidly over the last 8 weeks and giving us a very modest to low pasture production over the last 8 weeks. So looking at the rainfall record alone does not always give us a true indication for what's happening in terms of our pasture productivity. But what can we do to manage such variability in our rainfall? What can we really do? So let's have a look. The soil water balance is a conceptual model that helps us understand just how much stored soil water remains in the root zone of our pasture or our soil water account. By repeatedly measuring the soil water content and integrating rainfall, we can see how much of our rainfall that the pasture is making use of. And the diagram on the left-hand side is just a diagram of the conceptual model with all the different terms and arrows. So the arrows represent the direction of the water flow at any given point in time. The equation here is really the nuts and bolts of it. So the equation is delta S, or change in the soil water storage, equals the rainfall minus the deep drainage minus the runoff minus the evapotranspiration. So what we can see here is that we have 3 loss terms which are the nub of making the best use of the soil water balance. If we can minimize the amount of deep drainage, if we can minimize the surface runoff, and we can minimize the evaporation within the evapotranspiration, then that will give us the best opportunity for building our soil water stores and driving pasture production at any given point in time. Now, of these loss terms, the easiest one for us to target as managers is surface runoff. So let's have a look at that. Cut the losses. A picture is worth 1,000 words. This paddock is just near to Tamworth Ag Institute, and after a drought period, we had a single rainfall event. And as you can see, an abundance of surface runoff has occurred. It's transported both sediment, soil, organic matter, and nutrients into the contour bank, washing it away from the pasture higher up the slope. So I don't need to say much more about that, apart from that's just a clear visualization of the sort of losses that we're starting to talk about. And perhaps this is the greatest irony when we're coming out of drought. We're desperate to build soil water to kickstart our pasture growth. But when we finally get some decent rainfall, we often see that surface runoff takes place, takes the water away with it, takes surface soil away with it, takes nutrient away with it. In our environment, perhaps lucerne pastures particularly are quite prone to developing low ground cover in the dry times. And this has the potential to lead to excessive runoff and erosion. And as I've mentioned, the runoff really represents a missed opportunity for production and leads to unsustainable soil loss. So what can we do about that? Well, can we grow lucerne with a companion grass to increase ground cover and therefore reduce the runoff and erosion? Well, the good news is, from research done in the Evergrows program, is that lucerne grown in mixtures with tropical grasses can easily control the surface runoff and erosion. So this slide shows 2 panels of surface runoff curves, which were generated from a rainfall simulator in spring of 2010 and autumn of 2011. So the y-axis is the rate of runoff in millimeters per hour, and the x-axis is the duration of the rainfall simulation. Rainfall was delivered at 105 millimeters an hour, representing a solid thunderstorm for our part of the world, over 30 minutes. And the key point that I want to draw your attention to is the difference between the dark grey line, which is the Lucerne pasture on its own, which is steep and rapidly rising, and the dark green line, which is Lucerne grown in combination with tropical perennial grass, digit grass. So its slope is quite shallow and they reach a plateau. The fact that the green line reaches a nice stable plateau is telling us that all the simulated rainfall falling onto those plots was being infiltrated into the soil and down into the soil water store. And the beauty of growing that mixture in both spring and autumn was that the runoff curve was pretty much the same. The bottom panel shows the total amount of soil loss that occurred from those rainfall simulations, and you can see that the amount of erosion that occurred growing Lucerne in combination with the grass was much reduced from Lucerne on its own. So that's just a physical example, demonstration of some data there, just showing the benefit of ground cover in reducing our runoff and erosion. So the point of this slide is really just to summarise that there's been a large body of work by many researchers and producers over time showing that perhaps ground cover is king and litter is queen. It might be an old rule of thumb, but old rules of thumb tend to be just that because they work. So maintaining ground cover at a minimum of 70% level in most pastures gives us the best chance to minimise the runoff losses and maximise rainfall capture and storage. Now, I understand that we've got participants now from right over Australia and right around New South Wales. So depending on where you are and the landscape that you're in, that threshold number of 70%, it can be higher in the steeper country and it can be lower in the lower slope country. So it is variable depending on where you are and what sort of system you're in. So if the goal is to capture our rainfall and increase storage, we've got to recognise that, well, every day of the year, evapotranspiration is taxing our soil water account every single day. In Tamworth, in this part of the world, on a monthly basis, evapotranspiration always exceeds rainfall on average. So we need to maximise the amount of deposits that we can make into our soil water account to keep a healthy balance. In my research, at least, or our research, soil water content is our mainstay. And we estimate soil water content using both things like the neutron moisture meter on the left-hand side of the screen, and in more recent times, an electromagnetic induction meter or an EM38 on the right-hand side. In our research, we take measures of soil water content every 3 weeks, year round, and that helps us build a picture of soil water extraction and replenishment in our pasture experiments. And it's the frequent measurement of the soil water content that helps give us early warning for either a decline in future pasture growth rates or an acceleration in future pasture growth rate. So it's an early warning system which I can't recommend highly enough. Now, there's a lot of information on that slide, and I'm not going to pore over all of it, but to think about soil water dynamics under a perennial pasture, they're quite different to those that occur underneath an annual crop. The panel on the left represents 5 or 6 different pasture treatments, and each section is the soil profile down to a depth of 1.9 meters, with soil water content represented from 2011 through to 2015. The treatments are lucerne grass mixtures. And just to summarize, the blue areas represent high soil water content and the red areas represent low soil water content. It's from those data that I can then analyze the amount and the depth of soil water extraction that's occurring in our pasture systems from year to year. And in my experience, at least by measuring these things, what I tend to find is that once we have our pastures established and they're growing well, we tend to find that we don't return to this all blue condition, more or less regardless of the amount of rainfall that we receive. To return to the full blue profile with water refilled all the way down the profile is actually quite rare. What the best chance of that occurring is usually in a winter when our summer active pastures are either dormant or frosted and our rainfall has a chance to exceed the potential ET rate. But from those data, I can analyze it and gives me these fan graphs, what I call fan graphs on the right-hand side. And simply to summarize what they're showing is the difference between, the space between the two groups of lines. Well, that represents the amount of soil water content that's been removed by the pasture, and where they cross over in a statistical sense, that tells me the root depth or the maximum level of extraction in the soil profile. So from those data, I can quickly interpret how far down the profile pasture roots are growing, where they're extracting water from, or perhaps what might be limiting them. So there's a lot of detail there. I won't dwell much more on that. But what I get out of all of that is something a little bit more straightforward, which might be some truths. Our stored soil water follows a similar pattern year on year in our environment. And while rainfall is highest in summer, because we've got the summer dominant rainfall, the soil water content tends to be highest at the end of winter or early spring. April, May is usually our driest time in the soil water profile, and August, September is the wettest. So that red arrow shows the pattern that we typically see. So from around first frosts, we start accumulating soil water in the profile up to around sometime in September. I hope everyone just understands that that's the rainfall bars. I didn't explain that, sorry. It's just the monthly rainfall bars, and this black trace is the total amount of stored soil water in that particular soil, and that's a mean trace, an average trace over multiple years of record. So it's not just a single year, that's an average trace over a number of years of record. So what I can glean from that is, if that's the normal expectation, if we come out of winter and instead of the trace being up high at a high point in September, if the trace is somewhere down here, that forewarns us that spring is going to be short and there's not going to be an abundance of pasture growth leading into summer. So pretty much all of what I've worked through just now is trying to build up a bit of a framework around how I view pasture systems, how I view the going into and going out of drought, and how I view trying to manage our pasture systems in this environment. I now want to walk you through a couple of examples where I'll look at the data more closely from experiments that are currently running here at Tamworth Ag Institute. And this experiment is called the digit grass lucerne density experiment, which is being conducted underneath the Livestock Productivity Partnership together with MLA. Now, this experiment is really quite unique. It's unique because each of the 5 treatments has been established at a consistent plant density of 8 plants for each square metre. The 5 treatments are ratios of digit grass and lucerne to make up that 8 plants per square metre. So the first one is 0% lucerne, second, 25% lucerne, 50% lucerne, 75% lucerne, and 100% lucerne. And conversely, digit grass is the opposite. Now, the experiment was established in 2018, leading into the peak of the drought. So it's given us some really interesting opportunity to look at how those different pasture systems have reacted to the dry time and coming out of the dry time. To illustrate what the plots look like, these 4 slides are the 50% lucerne treatment in each of the 4 seasons. So top left is summer, quite a bit of growth there, but looking a little bit stressed and wilted. Autumn, the pasture is thinned down quite a lot. In winter, on the bottom right, we can see lucerne is green, but the digit grass is frosted off. And then back to spring again, with both species looking quite fresh. So since sowing in November 2018, we've been measuring soil water content to a depth of 1.9 metres every 3 weeks. So the resulting data gives us these traces of stored soil water through time for each of the treatments. At sowing, on the top left, soil water content was around 750 millimetres for all the treatments. And at the peak of the drought in late 2019, the 0% lucerne treatment here, for example, reduced total stored soil water down to 475 millimetres, giving us a plant available water of 275. So each of these traces is for each of the different combinations of lucerne and digit grass. The interesting point I want to make here is that the 0% lucerne treatment, i.e. no lucerne, all digit grass, was the treatment that lowered soil water content the most, whereas 100% lucerne was up here, just under 600 millimetres. So it's quite interesting that the common perception is that lucerne extracts the most soil water, and yet repeatedly I've seen in experimentation where digit grass will extract more soil water, at least from the top 2 metres of the profile, than lucerne does. Now, working through this, what I want to draw your attention to is the 1 and the 2. And these are the 2 little periods that I'll explore further now in terms of coming out of the drought. The first one, number 1, was our first major rainfall events at the end of 2019, early 2020. And the second one is the wet summer that we've just passed through. So at each of these points in time, I'm taking slices through the soil profile to see the change in the distribution of the soil water content at those specific times. And it gives us these fan graphs at those times. The x-axis is the soil water content on a volumetric basis, and the y-axis is the depth in the soil profile. The blue trace, the blue line trace, is the drained upper limit for the soil, and the orange line trace is the plant lower limit for each of the pasture species. The open diamond trace here is the soil water content on the 9th of January 2020, and the black circle trace is the soil water content on the 20th of February 2020. And the shift, or the change, is the captured water in response to the 237 millimetres of rain that was recorded over that period. So we can see there on the left-hand side that the lucerne 0% treatment, which is all digit grass, captured 144 millimetres of the 237 millimetres of rain. And on the right-hand side, the all lucerne treatment captured just 36 millimetres of the 237 millimetres of rain. And you can see in the lucerne treatment, the amount of capture, the depth of the penetration, how far down the profile the water went, was only down to about 0.8 of a metre, while for the digit grass, we accumulated soil water virtually the full depth of the soil profile from those rainfall events. So clearly, there was a starkly different response by these treatments to that rainfall event at the peak of the drought. But what happened in terms of production? This is very interesting. This is where it gets interesting. So the 5 photos across the top represent each of the treatments. 0% lucerne on the left, 25% lucerne, 50, 75, and 100% lucerne. The photographs were taken pretty soon after, a couple of days after the first major bit of rain, and you can see for yourself the difference in the ground cover on the plots. The table down below shows what I estimated was the ground cover for each of the treatments at that time. So 0% lucerne around the 70% ground cover mark, and the 100% lucerne maybe around the 30% ground cover mark. The next row in the table shows the amount of soil water store that we captured. So 144 millimeters for the 0 lucerne, sliding down to the 36. The subsequent amount of herbage production during this period, nearly 4,000 kilograms for the digit grass, sliding down to 800 kilograms for the lucerne. The proportion of legume that was in the mixture, obviously increasing to the 100% lucerne on the right. But interestingly, the water use efficiency, which is the ratio of the herbage produced per the amount of water used, all digit grass, 42 kilograms of dry matter per millimeter of water used, sliding down to lucerne at 4 kilograms of herbage mass produced per millimeter of water. So I think that's a clear demonstration there of the differing responses of those pasture treatments to those first major rainfall events coming out of the drought. But it begs the question, well, if the 100% lucerne treatment captured such a little amount of that 237 millimeters of rain, where did it go? Flash flooding was a common sight in the valleys around Tamworth at that time with the arrival of those first rains. So it's a classic demonstration of valuable water and nutrient loss at the critical time when we really wanted it, and that's going to lead to missed production opportunity. The second period that I wanted to go quickly walk through, same style, was the summer of December 20 through to March 2021. And over that period of time, we had 357 millimeters of rain here at Tamworth, the same pasture treatments to work through. So the same setup for the graphs. The 100% digit treatment accumulated 89 millimeters of water, shown by the blue shading, while the 100% lucerne treatment didn't accumulate any at all. It actually had depletion of minus 11 millimeters, but also interestingly, there was no soil water extraction by the lucerne in this treatment below a depth of 0.8 meters, which is quite fascinating given the conditions that we were in. So moving forward to the production slide, that shows you the condition of the pasture in, I think it was mid-December, at the time when we were doing our first cuts for the season. And we can see again, clear differences in the ground cover situation. Same sliding scale in terms of rainfall capture. And then when we look at the herbage mass, digit grass produced over 8,000 kilograms of dry matter, while lucerne produced a bit over 4,000 kilograms of dry matter for the same period. Now, what is interesting is that the 3 treatments in the middle with different combinations of lucerne ratio, that the 50% lucerne was probably the standout. Now, it's important to note here that the only treatment that receives nitrogen fertilizer is the all digit grass treatment. All the other treatments rely upon the lucerne to fix nitrogen for the treatment. So again, we see this sliding scale of water use efficiency from 30 kilograms of dry matter for the digit grass down to 11 kilograms of dry matter per millimeter for the lucerne. And again, it begs the question, if a treatment like 100% lucerne not only did not capture any of that 357 millimetres of water from this table, where did it go? And again, it was the same situation. We had creeks running with plenty of material in the creeks. So that brings me more or less to nearing the conclusion of the presentation. And I just wanted to update now, okay, if we're looking at our rainfall record again, let's update this table that I showed earlier in this presentation for rainfall values to the end of April 2021. So exactly the same structure. And now we can see that for the 12, 24 month accumulation periods, we're in surplus. We've had surpluses all the way down to a 30 months period, but for the 3-year period, we're still minus 171 in terms of our rainfall accumulation. So looking at those figures, you would say, yes, we're pretty much out of the drought, except for our longer term periods, we're still at quite a deficit. Okay, so that pretty much brings me to the conclusion of what I wanted to present. And obviously, this is a large body of work that's gone into generating this style of information. So across many, many programs, thanks to my colleagues and collaborators over more than 20 years. And there's some of the programs that have supported this work. So in terms of take-home messages, this is what I want to leave with you. Perhaps drought is far more frequent than you might think, because drought from a pasture production perspective is whenever there is a water shortage for the pasture growth. And that's not at wilting point in the profile. That occurs well before wilting point is reached. In terms of pasture production systems, I think rainfall capture and storage is the #1 goal, to make the most of soil water when we're coming out of any dry period, which virtually means all the time. Ground cover is the king and litter is its queen. Those two together will maximise the amount of rainfall capture and storage. And a question that I might like to leave you ponder is, wherever you are right now, how many millimetres of plant available water is your soil holding? And for that particular pasture type, how many days might it sustain pasture growth? So they're the sorts of things that are always going through my mind whenever I'm looking at our pasture experiments. So with that, I will conclude my formal presentation and welcome some discussion.
Thanks, Sean. Outstanding presentation. With Eli there, so I'll just ask Eli's question. I was just wondering if Sean knows of any relevant data for coastal northeastern New South Wales pastures. Just thinking about a drought resilience project we're about to start work on, and information like this for coastal situations would be great background.
Yeah, unfortunately, the short answer for me, Eli, is no. I don't personally know of soil water network information that is available on the upper north coast. There has been a range of experimentation done over years that I am familiar with, but at the present time, no, I'm not aware of an active system. And that's one of my key points of interest, is how do we get an information source that better informs not just the North Coast, but also across the state. If we had a network of information that could deliver, that would be a great resource.
Thanks, Sean. Thanks, Eli. I hope that's helpful.
I'm just thinking about Eli's question there a little more, and yeah, I took it literally. You know, is there a soil water network that provides information for that part of the world? And the short answer is no. But there are platforms available on the web that give us that style of information. So a platform that I often use is called the Soil Water app, and the Soil Water app generated from essentially in Queensland, but one of our DPI researchers was also involved in it. It generates for you a model, a soil water balance model of what the soil water content might be, or what the plant available water content might be for the specific paddock or area that you're interested in. So using that sort of platform, Eli, you could go directly to the area or the paddock you're interested in. It will collect the soil physical characteristics. It'll drag in the historical rainfall record, and you can pretty quickly get an appreciation for what the likely soil water status is at that point in time. So if you want to look that up, that's called the Soil Water app. Warwick Badgery might also have a comment or a question about some other things that are going on. But yeah, that's definitely a place to start.
Would something like the Farm Forecaster program, because we've had a presentation on that, be useful in that situation too, Sean? That's actually a collection of data.
Yeah, correct. Yeah, the Farming Forecaster platform in its present rollout is in southern New South Wales primarily. I'm actually working with the LLS for Northern Tablelands and Hunter, investigating getting a few farming forecaster sites set up in northern New South Wales, probably more around the Tablelands, Northwest Slopes, Hunter, mid-north coast. Don't know about the north coast. But yes, the Farming Forecaster is also a way of bringing together the soil water status information via direct measurement and modelling what the likely pasture growth outlook might be. So yeah, that's definitely another avenue, but it's very early on in development for northern New South Wales.
Terrific. Warwick Badgery's ears must be burning. He's got a question here.
How you going? Sean, just wanted you to comment about the role of soil water limitation, soil nitrogen limitations on soil water utilisation. So basically how that impacts the millimetre of stored soil water into kilogram of dry matter.
Yeah, that's a really interesting question, Warwick. Depending on where, what your background might be, I can start the left-hand side of the spectrum. If you're looking at a grass-based pasture, you can take the perspective that 100% of the time that grass-based pasture is nitrogen limited because it's a grass that needs to get nitrogen from somewhere. The only plant that's happy in that regard is the legume. Now, my experience, at least in our transiently dry landscapes, is that a way of describing it? In our drier landscapes, I tend to find that water is probably our dominant growth limiting factor in the main. However, on rare occasions, and I think this summer has been one of those rare occasions, where our tropical grass pastures ran out of nitrogen and therefore shut down their growth, regardless of water being available. So from my measurements and from my observation, my experimentation in these summer growing species, this year was one of the rare ones. This year was one of the rare ones where we had soil water available, but we ran out of nutrition. So the growth rate and the conversion of dry matter slowed right down. The slide that's on the screen right now is for production up to the 2nd of March. And I chose the 2nd of March because that was the end of the summer period. That's the main reason why I chose it. However, from 2nd of March to now, I can't remember the precise number, but the digit grass treatment has only grown 600 or 700 kilograms of dry matter, I think. It's really low. So the water was there, growing conditions were still okay, it was still warm enough, plenty of sunshine, plenty of available water, but it had depleted all of its nitrogen stores and just did not grow. So yeah, it's a relevant question where we need to match and this is where I think the management side comes in. If we have an understanding of the amount of water that's in the system right now, we can forecast how much nitrogen we need to feed it to get the maximum productivity and the maximum conversion.
Thanks, Sean. Thanks, Warwick, for your question. We're getting down to not many typed questions left. I'm going to just ask you mine, Sean, which is we did have a couple of attendees from the New South Wales Western Division, and
Yep.
I imagine we'll have quite a few more listen to the recording. So I just wondered if you could comment about that environment. The question was raised for me when you talked about the ground cover percent thresholds, and you did allude to those a little bit. Would you like to elaborate?
Yeah, so the ground cover thresholds that I sort of have ingrained into my mind are from the perspective of raindrops. So how much ground cover is required to protect the soil surface from raindrop impact and allow the infiltration to occur. In the lower rainfall areas like the Western Division, the ground cover threshold is not 70%, it's lower in general, and the main target out there is to prevent erosion by wind. Generally speaking, I think the value they like to use is minimum of 40% to keep the soil surface stable from wind erosion. I think Craig Strong is in the room as well, but he would obviously know the precise levels for wind erosion. So yeah, maintaining ground cover in the west is a real challenge, and that's why in terms of water balance, evaporation of water from the soil surface is such a big loss, and that's really hard to shut down in those lower rainfall areas with high evaporation demand. The simple rules of thumb of ground cover and amount of litter that I use are just way above what would be expected in the Western Division.
I suppose to push it a little bit further, Sean, you don't have to answer this if you don't feel it's appropriate, but any comments on soil water accumulation in that part of the state? Given your comments about going from 0% loosened to 100% grass, is there anything there of relevance?
Well, I think just thinking about it strategically, the period of time for soil water accumulation in those soils is obviously going to be the cooler months when the cold fronts come up from the Southern Ocean. So they're the times when the soil water has a chance to accumulate, but the soils are generally lighter out there as well. So you get a good rainfall event in summer, you can actually get some decent penetration into the profile because most of the soils are of a lighter nature. The heavier soils out there are much slower to react. They need a lot of rainfall to get them to go, as the producers out there know. So in my way of describing that, I use the saying easy in, easy out. So if the rainfall can get into the soil easily, well, usually it comes out easily. So a lighter soil, you get good infiltration, good penetration into the profile, but by the same token, pastures can easily extract the water from the profile. Whereas as a clay, you've got to have a much more sustained rainfall event. It's harder to get the water into the profile, and corollary is that the pastures actually work harder to get the water out of a clay soil. So easy in, easy out. The lighter soils in the west, they are very responsive to good rainfall events. The most likely time of accumulation is going to be in the winter months, the cooler months.
Sean, a lot of the people in this new Rangeland Living Skin project are talking pretty much universally about trying to maximise the amount of water they can get into the soil. As you know, there's a lot of scalding out in the Western Division. A lot of people are trying different water ponding techniques.
Yep.
Do you have any comments on that in terms of a water infiltration point of view?
Yeah, well, the water ponding, the purpose of the water ponding is to hold water on the soil surface for a long enough period of time that, in effect, you force infiltration. And that forcing of the infiltration can also lead to a bit of leaching of any salts that are accumulated in the surface soil and or the sodic nature of those subsoils. So yeah, the water ponding technique is primarily about holding water in the system longer to get some decent infiltration and change the chemical balance, I guess, in the surface soils. And when that happens, you get more opportunity for germination and establishment, and then it's a self-reinforcing cycle.
Fabulous. Thanks very much for indulging the rangelands interests. It's very topical for myself and a few others.
No, that's fine.
Look, I just thought that was outstanding webinar. Sean, you've made all these topics, once you get into the science of them, are extremely complex, and you have made them as simple as possible. And I'd like to thank you on behalf of the audience for the obvious effort you've made into putting your slides to making them as understandable as possible. Fascinating area, couldn't be more of interest to anyone in agriculture, this topic. So yeah, I'd just like to thank you on behalf of everyone and thank everyone for their attendance. Just did you want to say anything to sign off, Sean?
No, just obviously thank you everyone for your interest. If there are any questions or other discussions you want to have, feel free, contact me via email or telephone, and yeah, happy to have a discussion in future.
Thanks all. See you next month.
See you.